Hi, everyone. So I've spent a good chunk of the last year and a half working with the Kinect and working on the ROS drivers for the Kinect, and I'm here to tell you how awesome it is. But many of you already know that. The Kinect had quite a splash when it came on the market, late 2010. Sold millions of units. I think it was the fastest selling piece of electronics ever. And people in the robotics community got really excited about it because they said, this is the 3D sensor that we've been waiting for. Thing is, you really need 3D perception for robotics if you want to do anything beyond very scripted open loop behavior. So for example, if you want to do mapping and navigation, this is a map that's built by Octomap. You need 3D perception. If you want to pick up things, recognize objects, you also need to figure out where they are in 3D. Everything that we're doing in robotics is manipulating the real world. So we need it, but 3D perception is hard and it's been expensive. I mean, the entire field of computer vision basically exists to turn 2D images into 3D inferences about the world. And we have all kinds of technologies for doing this. We have stereo, we have time of flight, we have structured light. We also have laser scanners, of course. Some of these work better than others, but they've all been hard to do and have been costly. And then the Kinect came along, and it's $150. So what are we looking for in a 3D sensor? So here are 4 things that we'd like. Cheap is good. The more resolution, the more detail you get. The Kinect is 640 by 480, which is actually pretty good as these things go. Speed is important if you have any kind of movement or dynamic scene. You know, there are technologies that give you very accurate 3D scans. Like on the Pure 2, we have a Hikoyo laser on a tilt platform, which gives you a very rich set of accurate 3D data, but it takes a few seconds to collect that. If you have a moving object in there, it's gone by the time you've seen it from the data. And under quality, I lump in things like coverage of the field of view in terms of the actual depths you get, the accuracy and precision of the depths. And the Kinect does pretty well in all of these categories, especially price. It was really an outlier when it came out. This is a very active area of hardware research, so I'm hoping that we'll see more devices coming out that are comparable or even better. But for the last year, the Kinect has really been where the game has been at. And just one example of what this has enabled. A couple of years ago, you would have been lucky to spend $1,400 and get a decent sensor. Now you can get an entire robot with a mobile base and a little bit of processing power. So a few months after the Kinect came out, we'd been hacking away like crazy to build up support for it in ROS. We did a 3D challenge where we did a call to the community, do something cool, make a video, send it to us. We awarded prizes. And so a bunch of people did exactly this. I'm just going to show a few of the videos that came out of this. At the bottom right, this is a video from Garrett, who's here somewhere. This is an early BillyBot prototype that's following him around by using the skeleton tracking capabilities that made the Kinect so attractive for gaming. Up top, we see also using the skeleton tracking, a teleoperation of a humanoid robot. And on the bottom left, you can even mount one of these things on a quad rotor, and here it's being used to travel down a corridor, staying safely in the middle without veering into the walls of the ceiling. So the rest of the talk is going to be in 3 parts. First, I'm going to go over the hardware, so how the Kinect actually works and what that means for you as a user, and how we get data off of it. Then I'm going to talk about how it's integrated in ROS, what the driver looks like, what are all the tools that you can use. And I'll end by giving you some flavor of what you can do with our 2D, 3D processing libraries, in particular OpenCV and PCL. So this is what the Kinect looks like if you manage to rip the skin off of it. There's an IR camera up there on the right and an IR projector. Those are the two components that are actually used to compute the depth. And also, because we all love color images, there's an RGB camera. Well, that's not used for depth sensing. So to briefly review how conventional stereo works, because it's relevant, you see some point out in the world from two cameras, the left and the right camera, and you're trying to detect its depth z based on triangulation. So you know there's some baseline distance between the cameras t, and because the cameras are separated, that point out in space appears on their image plane slightly offset in the two images that you get. So these cameras, they're calibrated so that their image planes are parallel to each other. And you can correlate some point between both images and say, oh, well, it shifted a little bit between the left and the right. And that's called, that value, that shift amount is called the disparity. So here it's x1 plus x2. And if you work out the similar triangles here, then you find that you have a very simple formula for distance. It's proportional to the focal length, the distance of the image plane, and the baseline. And it's inversely related to this pixel disparity that you detect by matching pixels across the images. So on the Pier 2 pre-Kinect, we had actually two pairs of stereo cameras. This was about the best we could do at the time. And we added one more element there, which was this texture projector. So this is a passive vision system. It's just taking light in from the world. And now we're turning it into an active one, where the point of this is that if you point a passive stereo system at, say, a blank wall, you can't match anything up between the images, so you don't get any depth. But if you project some texture onto it, well, now you have something for the correlation algorithm to hook onto. And then PrimeSense, which is the company that developed the depth sensing technology, that Microsoft licensed for the Kinect, they had this very nice insight that if you're already projecting texture onto the scene, you actually don't need the right camera. You can kind of use the projector itself as your right camera. And so what they're doing is they're projecting this IR speckle pattern out into the world. And during the factory calibration, you point this at some wall that's a known reference distance r away, and you record an image of what the speckle pattern is. And this takes the place of your right stereo image. You just put this in flash memory on the camera, and then you take the image that you got from your IR camera, do the exact same stereo correlation kind of stuff. You get some shift value s in the reference plane, and you can turn that into a distance. So it's very, very, very similar to stereo, and a lot of the conclusions that you can make about stereo also apply here. And finally, because there is that extra RGB camera, there's an extra calibration step to take the depths that you've detected in the IR camera and reproject those into the RGB camera frame if you want those to line up right. So we did some rough experiments to figure out how accurate this thing is, and it's pretty good, actually. We couldn't really detect very much error, like maybe plus or minus a millimeter relative error within the meter and a half to 6 meters where you get good information. Measuring with a tape measure and doing a pose calculation from a checkerboard, it's pretty much within the range of error that we could detect. It can be biased, some systematic bias up to a centimeter. You really only notice that if you're calibrating it to one or more other cameras and you're trying to figure out why the depth is a little bit further or shorter than it should be. I'm not totally sure why that is. Maybe just PrimeSense and I disagree a little bit on where the optical center is. Most of the time you won't notice that though. And for stereo systems, the error in the depths that you get increases quadratically with the distance. And we see exactly the same thing with the Kinect, since it's essentially the same principle. So here we're fitting a couple of curves to the error that we detect by pointing the Kinect at a plane, fitting a plane to all of the data, and then seeing how much the points vary from that. What this chart also shows is that because the Kinect is active, if you have two Kinects looking at the same scene, that IR speckle pattern from both of them can interfere with each other. And so that increases your error also. It's not too bad. For many applications, this is probably okay, and it may be useful to get that extra data. Lastly, I just want to mention a couple of gotchas with USB. I've seen a bunch of people get excited with actually putting multiple Kinects into the same system, which you can do, but there's some challenges there. For one thing, these things are just firing data at the computer. If you're streaming RGB in depth from a Kinect, it's basically taking an entire USB bus to do that. So you can only get 2 streams over one USB controller. So if you want all of the streams from multiple Kinects, you need multiple controllers. If necessary, you can add them via expansion slots. And for some reason, USB 3, the new USB standard, doesn't really seem to work with these things. I don't know why. It may be a firmware issue or something. So watch out for that. So I keep saying Kinect, but that's actually not your only option. Asus has come out with an almost identical device. It's the same technology, licensed from PrimeSense. You can use the same drivers with it. And so here's a little rundown of the relevant differences. I like the Asus. It's a smaller form factor. It runs just off USB power, whereas the Kinect has this weird proprietary adapter that you also have to plug in. The Kinect has a tilt motor and an accelerometer. Most of the time we're doing a fixed mount onto a robot where we already have other sensors to take care of that, so we don't care. And also the Asus has a couple of nice hardware capabilities from PrimeSense reference design that Microsoft ripped out. Asus can actually do the registration, putting the depth image into the RGB camera frame in hardware, which is nice, saves you some software computation. And can also synchronize those 2 data streams, which is also important if you're doing a lot of movement or trying to detect moving objects. The Kinect has a bigger microphone array, if you care about that. And then recently, Microsoft's put out this Kinect for Windows device, which is pretty much exactly the same thing, but $100 more expensive. And then to briefly look at the driver libraries that you can use. libfreenect was the first on the scene. Like right after the Kinect came out, people started trying to hack it, and very quickly were successful. So the very, very first ROS driver that we did was libfreenect based. Works now with Kinect for Xbox and the Asus cameras. It gives you the data streams. It's nice for hacking because it's small and simple. You can dive down just a little bit and get straight to the USB calls. In ROS, we're actually now using OpenAI, which is an open source project from PrimeSense. So this came out like a month later, and it was like, oh my God, now we have the answer key. Like we don't have to do any more of this reverse engineering. And it has some more nice features. It has skeleton tracking. And then there's the Kinect SDK from Microsoft, which was late to the party. I haven't really looked at it very much. Currently, it's the only thing that does the Kinect for Windows device, although that could be added to the open source libraries. It also has skeleton tracking, of course. The big distinguishing feature of the Kinect SDK is it can do some interesting things with the microphone array. So source localization, speech recognition, whereas the other libraries don't really have a good story for that. But there is another open source library that does. There's this library called HARC from Japan that does open source robot audition. And they've actually reverse engineered the Kinect audio devices. So they can bring those in as a Linux ALSA device and do these kinds of source localization, speech recognition features. And they're also in ROS too, which is nice. Okay, so that was the hardware. Now we'll talk about what this looks like in ROS. So here's the stack layout that's relevant and the dependencies. This is, as of Fuerte, there's some movement between Electric and Fuerte. So in Electric, the three OpenNIs, tracker, camera, and launch, were all packages in the OpenNI Connect stack, and the dependencies weren't as nice and separated as they are here. In Fuerte, all three of those are now unary stacks. OpenNI Connect is basically empty. It's a meta stack that depends on all three of those. And then all of the processing that requires our big libraries like OpenCV and PCL is pushed out into the image pipeline. So OpenNI Tracker is basically a very simple wrapper around OpenNI's skeleton tracking, and it publishes all of the joints that the skeleton tracker sees to TF, which you heard about earlier. So that, this is the kind of thing that a couple of those hacks we saw earlier were based off of. And then OpenNI Camera is the camera driver. So it, I hope, follows all of the best practices that we heard about. It's very minimal as of Fuerte. It just publishes the raw data streams. It's following this principle that you should take as much processing as you can out of the camera driver, so you can reuse it with other cameras, and also simplifies the camera driver, which is still pretty complex for the Kinect. So you get the raw Bayer YUV RGB stream, depending on the device. You get the depth stream. OpenNI's format is 16-bit integer depths in millimeters. In the rest of the ROS, we use floating point depths, but it's okay. And you can also get the IR stream, which you need it, which you really never do unless you're calibrating. And then you see there are two namespaces for depth and depth registered. Those to me are semantically different. And in the driver, OpenNI will actually do the registration for you based on the factory calibration, which is nice. And if you're using the ASIS, that will even happen in hardware, which is even better. So to enable that, you just use dynamic reconfigure, bring up the drivers panel, and enable this depth registration checkbox. And so you can see it kind of crumples up that depth image a little bit to make it match up with the RGB image. Then image proc is part of the image pipeline. This does basic 2D processing of camera images, things like debayering and YUV conversion, rectifying images to correct for distortion. And then the new stuff is in depth image proc. So this was all written for the Kinect, basically. So a couple of things we'll do is take a depth image, convert it to disparity, if you need to interrupt with stereo processing nodes, or to a point cloud. And it will also, if you have a good calibration, so the internal camera parameters and the transform between two cameras, it can register a depth image to a new camera frame. So this is exactly what OpenNI is doing for the Kinect IR and the Kinect RGB cameras. And then you can combine that with an RGB image and get a nice color point cloud. So depth image proc was written during development for the Kinect, but depth images now are well defined in ROS. There was an REP about them. Depth image proc is an image pipeline. So this is perfectly usable with any other depth device that you care to write a driver for, whether that's stereo or time of flight or whatever, anything that'll produce a depth image. And this is all written as nodelets. So we just heard a little bit about those. This is very important to actually make all of this efficient. So then OpenAI launch, basically its job is to combine all of these nodelets into some coherent system. And if you saw my lightning talk yesterday, if you want to see all of those tricks taken to their logical or not so logical conclusion, you can look in OpenAI launch, which has a whole set of launch files that build up this computation graph using nodelets. It'll also provide a default TF tree linking the cameras on the sensor. In Forte, that's optional. You can sub in something better based on calibration if you want to. And this command is basically what you use to bring up the Kinect. And it's very easy. It publishes a bunch of topics, so you can check out the reference API. But these are the ones that you would commonly actually use. You have the point cloud topics with just XYZ or XYZ RGB. You have your RGB images. Generally, when you're processing, you should always use rectified images so that projection actually works correctly. And also the raw depth images, if you prefer to work on those directly. So this division into nodelets, this wasn't always how it was. In Diamondback, the Kinect driver was this monolithic thing that did all of the processing in one node. And this proved to be pretty inflexible. Like there were use cases that just weren't satisfied by that. Something that I've heard several times that people want to do is have the driver just run on some resource-limited device and do all of the processing on a separate, beefier computer. And you can do that, actually, quite easily with the nodelet-based ROS OpenAI driver. So you run the OpenAI node that's just wrapping the minimal driver nodelet on your resource-limited device. And then you do OpenAI launch, but tell it not to load the driver. This stuff is Forte. You can do the same kind of thing in Electric, of course, but it just looks a little bit different. And recording bag files looks very similar to that, actually. When you record a bag file, you want to record the raw topics. A lot of times your first instinct is to record the point clouds, but those are huge. They're bandwidth hogs. And in fact, if you try to record XYZ RGB, you actually can't write them to the hard disk fast enough as they're coming in. But the image raw for the Kinect is Bayer, so it's 1 byte per pixel. The raw depth image is 2 bytes per pixel. So this is very handleable. And if you really want to bring that down even further, you can use the compression facilities offered by Image Transport. So with the RGB, you can use whatever compression you want. With depth, you should really the only suitable thing we have is PNG for lossless encoding. Compression techniques for color don't really map so well onto depth images. They're not designed for that. And there's a tutorial for how to do this in OpenAI launch. So I spent a bunch of time working on Kinect calibration, so I'm going to talk about it a little bit. But most of the time, you actually shouldn't do this. The factory calibration that's baked into the Kinect is actually pretty good. So there are only a couple reasons to calibrate. If you want to squeeze out like that last little bit of accuracy, maybe you can do a little bit better with the user calibration. Or if you want to calibrate the Kinect to other cameras in your system, then this becomes interesting, and we have tools to do that. So first thing you always need to do is do the intrinsic calibration of all of your cameras. These are the internal parameters that tell you how to project some point in space into the image plane. And, oops, yeah, here we go. So we have a GUI tool and the camera calibration package that will do this. You need a checkerboard target. You get a bunch of views for it. And it knows the dimensions, and it can calculate focal length, optical center of the image, distortion parameters based on those captured images. With the IR camera, you have to be a little bit careful because that speckle pattern will mess up your corners on the checkerboard. But you can just like put a post-it over the projector, and it kind of diffuses it out, and it works. And then the extrinsic calibration, when you have multiple cameras, it gets interesting. I'm skipping slides here. So here's a simpler setup. What we did here is we have a 5 megapixel Prisilica camera mounted directly underneath the IR camera. You might want to do this if the RGB camera that's built in just isn't cutting it for you. So this way we got a lot more resolution and a lot more control over what the RGB camera is doing in terms of white balance, exposure, all of these nice things. Or you can go really nuts. This is a setup where it has 2 Kinects, 2 Prosilicas, and then a webcam just for kicks. And I don't know if you can actually see in the RViz window, but this stuff actually is calibrated to each other so that it looks like it all meshes together pretty well. So the tool that we use to do that is in the camera pose stack. And basically what you do is you take a checkerboard and you hold it very, very still. And this server finds the checkerboard in all of the images and finds a time interval where it's still in all the images, so you get a really robust view of it. And then each time you get a new view, it reruns this optimization to refine where the cameras are with respect to each other. And it publishes all that transform tree over TF. So you can actually do live calibration even on your running system. So just to summarize that part, what does ROS give you? You get easy device access. You get great visualization tools. You have data logging and playback through bag files, compression with image transport, calibration with multi-camera support if you need it. And getting into the last part of the talk, it integrates nicely with OpenCV and PCL, and all of the OpenAI niceties are dealt with for you. So for actually processing all this data, we have a couple answers for that also. There's OpenCV, which has been around for a long time for 2D vision, and PCL, which is new and exciting for 3D vision. So OpenCV, it's got tons of stuff in it, all kinds of general image processing, transforms, a bunch of the 2D stuff that I've showed here, like debayering, rectification, most of the camera calibration, that's done through OpenCV. The thing is, the OpenCV really is for 2D vision, so that you can use it to your heart's content on the RGB image, do all kinds of interesting processing on that. And it's tempting to process the depth image directly, because this, in many cases, this could be faster than working on this bigger point cloud. You have to be careful, though. Most of the algorithms in OpenCV that you might want to use won't do the right thing out of the box on depth images, because they aren't written to handle invalid points. And in any depth image, you're going to have a lot of invalid points. And you also don't want to do things like blur over depth discontinuities. There is one exception that I want to point out, though. The newest version of OpenCV that's in Fuerte has this line mod object recognition algorithm that one of our interns, Stefan Hinterstoister, devised. And this is very cool. This is working on the RGB image and the depth image. It's multimodal. It detects color gradients in the RGB image, detects normal gradients, or well, normals, in the depth image, and does template matching over both of those at the same time. And it's extremely fast, and you can see it here working well even on these very untextured objects, which most methods for doing object recognition on color images just fail on, because there's not a lot there to find. But if you have depth, then you can actually see the boundaries, and you can do a lot better. So most of the time for 3D processing, PCL is where it's at, the point cloud library. This does all kinds of awesome things for you. 3D features, object recognition, has some spatial data structures like KD trees and octrees. If you have multiple 3D point cloud views of a scene, you can register to those to each other and combine them. You can fit planes and cylinders and, I don't know, other connects to point clouds, and it has some nice segmentation capabilities too. So I've just got some videos that show off what PCL can do. This is Kinect Fusion. This is an algorithm that came out of Microsoft, and there's an open source implementation of it in PCL. This was cooperation between people at Willow, people at NVIDIA, and some of our OpenCV developers in Russia. And what it's doing here is you can see, the color image, just for reference. On the bottom right, the actual depth image that it's getting in, and then it's fusing that data over time to get a really nice reconstruction of the world in the top right. And this is being done in real time. All of the heavy computation is being done on the GPU. And here's some work from another one of our interns, Julius Camerol. He developed an octree library for PCL, which is this spatial structure. So you divide your point cloud into space, and then those 8 regions into sub-8 regions. And this is kind of like a binary tree for looking up 3D locations, finding what points are around it. And his interest was in compression. So he actually came up with a very neat compression algorithm using this octree, and then was able to further use it for doing compression over time by detecting which points have actually changed from frame to frame. And so here what you're seeing is actually a cross-Atlantic 3D Skype session, kind of, where they're using this compression to send the Kinect 3D video feed to each other. So very cool. And finally, this is some of the most recent segmentation stuff from PCL. Right now it's doing planar segmentation, so it's finding the table, the computer screen, and in a second it should turn on object segmentation. So it's finding the things that are sticking up from the planes and fitting nice little regions to those. And of course, these are nicely integrated in ROS. There are some bridge packages, CV Bridge, PCL ROS, for matching ROS messages to the native data types. And in fact, the PCL point cloud type is actually registered as a message in ROS, so you can pass shared pointers to PCL point clouds around directly. So we heard about nodelets. It's great to use them whenever possible. Point clouds are huge, images are also big, so for the best efficiency, one thing you can do to optimize is write your code as nodelets and load them into the same manager that's running the Kinect driver and all of the other processing that's going on. And so as I said, the Kinect is just like a fire hose of data to your computer. So nodelets are one way of optimizing, but often what you want to do is just turn down that stream, make it a little bit easier to handle. So there are a few ways that you can do that. Best of all is to do it on the device itself and hardware. So you can get down to a 320 by 240 image, I think, at least on the ASUS. And in parentheses, I have cropping. This isn't actually implemented in the ROS driver. It would be nice if it were. OpenAI has some cropping capability that I hope is actually implemented in hardware on these devices. And if you can reduce the frame rate in hardware, it's nice to do that too. I don't know that the Kinect or the Asus actually let you do that very much. Alternatively, in the driver, you can just drop frames. And so in dynamic reconfigure for the driver nodelet, there's like a data skip parameter that you can use to just have it drop frames in software and not do any further processing on those. If binning or cropping in hardware isn't working for you, you can also do that in software. ImageProc has a crop decimate nodelet where you can do decimation, basically throw out the points that you don't need, or you can do a better resizing operation from OpenCV and crop it. That is actually kind of nice for Bayer images. If you subsample Bayer, or if you do binning on Bayer images in hardware, you average out all of your color samples, so you just get a monochrome image. But if you do it in software, then you can pick and choose the data that you need and still get color. And finally, you can use PCL to downsample the point cloud that you get with voxel grid downsampling. And this is nice because it actually does downsampling in space, and so you get a much better like distribution of downsample points for PCL's processing purposes. But the further down you get on this diagram, the more you've paid in CPU time. So thanks for listening. Any questions? Okay, so the first question was, how can you skip the surrender step when using the tracker? So right now, to initialize the tracker, you have to do like this surrender pose so that it sees you. And in the newer versions of OpenAI, this step has been lifted. Unfortunately, the version of OpenAI that's used in ROS right now is old enough that it doesn't have that new feature that you don't have to do the surrender. So I don't know. That version will get updated at some point. With the newer versions, we had some issue with multiple connects, so we weren't in a big hurry to do that. And the second question was if you want to get just like one image on request, right, instead of subscribing to the stream. So there are a couple of answers to that. You can do like a ROS wait for message in ROS CPP. There's some function call where it wraps it up. It basically creates a subscriber, waits to get a message in, and immediately unsubscribes. So you can do that. You can also do that on the driver side. In fact, there's an API defined for this, the pulled camera API, where you do a service call requesting the driver to send an image on some topic. So far, I think the Priscilla driver is the only thing that actually implements that. It's really intended for high resolution cameras where you want to do like some very finely controlled like binning and ROI kind of operations. Okay, yeah, so pointing out that PCL, if you go to like the PCL PPA and get their version of PCL and all its dependencies, they have a more recent version of OpenAI in there, so you can try it out from that. PCL has its own implementation of skeleton tracking. Okay, PCL has skeleton tracking. Yeah, that demo is someone holding a Kinect in their hand and waving it around a scene. It's the only sensor that's being used. And so it's collecting point clouds, registering it to its scene before, and seeing from what it sees across multiple views, it's guessing at what the true geometry is. And there's a paper on that from Microsoft that you can check out for details. So does the ASUS work on USB 3.0? I'm not sure about anything with these devices in USB 3.0, but I think that people have had problems with it. What was the first part of the question? Oh, for HARC. So for HARC localization, what's the accuracy like? I actually don't know. I haven't tried that out myself. Right. Yeah, when we were doing this like crazy like calibrate 5 cameras to each other kind of thing, we would find that like everything worked out nicely except the depths would like point out a little bit further than they should. And we didn't, like, that was like the one piece that we didn't really have control over because we were getting the depths from OpenNI. And so what we ended up doing was adding some parameter to dynamic reconfigure where it just applies some constant offset to the depths that you get. And then everything lined up very nicely. Yeah, if it's like a keyboard or something, maybe. But like Kinect, if you're streaming like both data streams from the Kinect, it really does pretty much take over that controller. Oh, so a good question. Can you control the motor and the accelerometer in the Kinect? And that's not exposed in OpenNI, but libfreenect does that. And in fact, you can use those functions side by side. So you can use OpenNI to stream all of the data, and then the accelerometer and the tilt motor are separate USB devices. So there's actually a ROS package for this called Kinect Aux, Kinect AUX, and that should let you get to the accelerometer data and the tilt motor.